Welcome to this explainer. Okay, so as we barrel toward the massive 2026 shift in global energy security and industrial decarbonization, we're facing a really stark reality. The volatility of renewables, the simple fact that the wind doesn't always blow and the sun doesn't always shine, means we desperately need a clean, massive-scale energy buffer. And hydrogen, well, hydrogen is that ultimate clean energy promise. It burns completely pollution-free, and it packs just a massive energetic punch. But there's a catch. There's a major missing link that's preventing the hydrogen economy from truly taking over, and it has absolutely everything to do with how we store it. So today, we're exploring the absolute cutting edge of solid-state chemistry to see exactly how we're finally solving the single greatest bottleneck in modern energy.
Okay, let's dive right into this. To really understand the problem, you just have to look at this number. At 0 degrees Celsius, at standard atmospheric pressure, hydrogen has a density of just 0.0898 grams per liter. It is literally the lightest, most rebellious element in the universe. In its natural gaseous state, getting an energy-dense amount of hydrogen takes up an enormous, completely impractical amount of space. And honestly, this severe physical limitation is the exact reason why you don't already have a hydrogen-powered car sitting in your driveway. We simply just haven't had an efficient, safe, and compact way to lock it down.
Section 1. The taxonomy of containment. Basically, how do we store this stuff? To tame this incredibly rebellious element, scientists and engineers have basically developed three primary arenas of battle: physical, chemical, and material-based storage. And this evolution brilliantly illustrates a huge shift in our scientific thinking. On one hand, we're dealing with macro-level brute force, massive, heavy physical tanks just trying to force gas molecules together. But the direction we're moving, we're heading toward elegant, microscopic, perfectly ordered structures. We're talking about interstitial hydrides, complex hydrides, and advanced sorbents. It's a complete paradigm shift from fighting hydrogen's physics to actually cooperating with its chemistry.
Section 2. Physical storage. The brute force methods.
Let's start with what we currently use. To make gaseous or liquid hydrogen practical for transport right now, we have to subject it to incredibly aggressive, intense engineering. We aren't just talking about simple metal cans here. To hold compressed hydrogen at up to 700 or even 800 bars of pressure, we have to engineer these intense Type 4 tanks. You've got a high-density polymer liner acting as a gas diffusion barrier, and that is wrapped in a massively thick carbon composite shell just to provide the mechanical strength so the whole tank doesn't rupture. Obviously, this adds immense weight and complexity to the whole system.
But beyond the weight, there is a massive energetic penalty to this brute force approach. The laws of thermodynamics are totally unforgiving here. If you want to compress hydrogen gas adiabatically, it costs you about 16% of the energy actually contained within that hydrogen. And if you want to liquefy it, forget about it. You're spending around 30% of its lower heating value just to run the cryogenic coolers, and that's not even mentioning the constant boil-off losses. We are literally wasting a huge chunk of our clean fuel just to store it.
Section 3. Chemical carriers, specifically LOHCs.
Because that physical storage is so inefficient, researchers pivoted over to chemistry, specifically liquid organic hydrogen carriers, or LOHCs. The idea here is really clever. Reversibly bind hydrogen into an organic liquid that you can transport safely at room temperature, honestly just like gasoline. You load the liquid with hydrogen, ship it, and then unload it at your destination. Structures like dodecahydrocarbazole represent the absolute top tier of these carriers. These carbon-nitrogen rings are total champions at soaking up hydrogen. But, yep, there's a catch. Extracting the hydrogen back out is highly endothermic. It requires elevated temperatures well over 200 degrees Celsius. So while transport is a breeze, releasing the gas drains precious energy and requires super complex onboard thermal management systems.
Which brings us to Section 4. Solid-state storage. This is the innovation edge.
This right here is the true technological holy grail: material-based solid-state storage. Imagine a safe, solid powder that just pulls hydrogen into its microscopic pores, holds it there incredibly densely, and then releases it purely on demand with minimal energy loss. Now, to understand how these materials actually hold the gas, it comes down to a fundamental dual nature: physisorption versus chemisorption. In physisorption, the hydrogen molecules weakly cling to the surface of the material using physical forces in the milli-electron-volt range. It's fast to load, fast to unload, but it usually requires really expensive cryogenic temperatures to stick. Now in chemisorption, the material literally breaks the hydrogen molecules apart and forms strong chemical bonds, up to 4 electron volts. This packs the hydrogen incredibly densely, but it requires a lot of heat to break those deep bonds and release the gas.
So, to bridge this gap, scientists are turning to a fascinating class of materials known as metal organic frameworks, or MOFs. And the absolute best way to visualize MOFs is through this metaphor. They are like a magnetic sponge for gas. They feature extraordinary permanent porosity and massive internal surface areas. Seriously, just a few grams of MOF powder can have the internal surface area of an entire football field.
If we examine the underlying crystalline structure, an MOF is this interconnected network made of organic linkers acting as struts and metal nodes acting as the joints. By chemically tuning these struts and nodes, scientists can design perfectly sized microscopic pores that specifically attract and hold intact molecular hydrogen. It is molecular architecture at its absolute finest, allowing for a really high uptake of hydrogen without needing extreme pressures. And we can actually push these MOFs even further using a phenomenon called hydrogen spillover. By immobilizing metal nanoparticles like palladium onto the MOF surface, the nanoparticle acts as a catalyst. It attracts the hydrogen molecule, splits it into individual atoms, and then those atoms literally spill over and migrate deep into the surrounding MOF structure. This massively enhances the storage capacity far, far beyond what the MOF could ever achieve on its own.
Now, on the chemisorption side of solid-state storage, we have metal hydrides. Light element alloys, particularly magnesium-based hydrides like MgH2, are incredibly attractive. They pack a dense punch, offering a gravimetric capacity of 7.6% by weight, which is fantastic, but thermodynamics is a strict master. They hold on to the hydrogen so stubbornly that you literally have to blast them with temperatures over 500 degrees Celsius just to force them to release the gas. That thermal hurdle really limits their use in everyday vehicles, which sets the stage perfectly for advanced computational discovery to find that perfect middle ground.
Section 5. Unlocking the future through computational discovery.
We are no longer just mixing chemicals in a lab and hoping for the best. We are using AI and quantum topology to custom design materials, literally atom by atom. Just consider this alien-looking marvel. This is the Saturn-like charge transfer complex, known as lithium-4 boron-36. Recently discovered through extensive first principles theory calculations, this specific geometry features a boron core with 4 capping lithium atoms. Computations reveal that each single lithium atom can bind exactly 6 hydrogen molecules in a stable state. It's a total masterpiece of computational discovery, sitting right there in the perfect sweet spot between weak physisorption and strong chemisorption.
If we treat these gravimetric densities like a high-stakes race, the promise of these engineered materials becomes undeniably clear. The U.S. Department of Energy set a very strict practical benchmark for solid-state storage at 6.5% gravimetric density. As we just discussed, magnesium hydride clears that at 7.6%, but it fails on temperature. But look at the predicted capacity for our Saturn-like boron-lithium cluster, a staggering 10.4% by weight. I mean, if we can synthesize and scale complexes like this, it completely changes the math of the entire energy transition.
And the discovery of materials like the lithium-boron complex, it isn't a fluke. It's the result of an accelerated future driven by automated computational tools. Researchers are out there conducting high-throughput screening of over 13,000 different MOF topologies simultaneously. They are using molecular simulations to predict adsorption dynamics long before a material is ever physically created in a lab. Combined with nanoparticle functionalization, software algorithms, and molecular engineering are rapidly, and I mean rapidly, accelerating the discovery of the perfect hydrogen lock.
Which brings us to the ultimate question. The production of green hydrogen is scaling up right now, and fuel cell technology is totally proven. The bottleneck has always been storage, how to pack it safely, densely, and efficiently. So if computational materials science can finally provide us with the ultimate solid-state lock to store and release hydrogen on demand, how fast can we build the zero-emission economy of tomorrow? Solving this single microscopic puzzle could be the exact trigger needed for a massive global energy revolution. Thanks so much for joining me on this explainer, and keep